Hello and welcome to another video on partial fraction decomposition. This video addresses the question of whether irreducible quadratic factors are indeed necessary. So our objective is to compare partial fraction decomposition procedures when applied to irreducible quadratic factors over the real numbers and then again over the complex number system. So we're going to consider this problem. X squared plus x plus 1 divided by the product of the factors x squared plus 1 and then x plus 1. So we have the following calculation over the real number system. We have an irreducible quadratic, x squared plus 1. So we're going to give that a linear structure in its numerator, ax plus b. And then we have a distinct linear factor, x plus 1. And we're going to give that a constant structure on its numerator with just representing by c. So we combine those two fractions together, and we have as our result of x squared plus x plus 1 equals to the quantity a plus c times x squared plus the quantity a plus b times x plus the quantity b plus c. And this is matching up the numerators. So to set up our system of equations, we have the following. The coefficients of x squared have to match. So we have 1 is equal to a plus c. We have the coefficients of x. They have to match, and that's 1 is equal to a plus b. And then we have the constant terms, and they have to match. And that would be 1 is equal to b plus c. When you go through to solve this system, you get a equal 1/2, b equal 1/2, and c equals 1/2. So over the real number system, the partial fraction decomposition of x squared plus x plus 1 divided by x squared plus 1 times x plus 1 is going to be 1/2 x plus 1/2 divided by x squared plus 1 plus 1/2 divided by x plus 1. Let's consider the same example, except this time we're using the complex number system. And this means that when I take x squared plus x plus 1 and divide it by the quantity x squared plus 1 times the quantity x plus 1, I can rewrite this as x squared plus x plus 1 divided by the quantity x plus I times the quantity x minus I times the quantity x plus 1. And that's because x squared plus 1 is the sum of squares, and we can factor the sum of squares over the complex number system. And it factors into x plus I times x minus I. Remember, I is the square root of -1. So using the format for distinct linear factors, our rational function in its completely factored form can be written as a divided by a plus x plus I plus b divided by x minus I, plus c divided by x plus 1. Recombining this template has the numerators match up as x squared plus x plus 1 is equal to a plus b plus c times x squared, plus the quantity a minus ai plus b plus bi times x, plus the quantity negative ai plus bi plus c. Matching up the coefficients for this decomposition gives us the coefficients of x squared matching up as a plus b plus c is equal to 1. The coefficients of x, a minus ai plus bi is equal to 1. And the constants have to match up as well. Negative ai plus bi plus c equals 1. Now, this system can be solved by using any of the methods that you're aware of, but the complex numbers involved in this system can make it a little unwieldy. So let's introduce a new theorem, and that's going to make this a little bit simpler. We introduce the partial fraction decompositions coefficient theorem. We're going to let p of x over q of x be a rational function, where p of x and q of x are polynomials, such that the degree of p of x is less than the degree of q of x. In other words, this is a proper rational function. If x equals a is a root of q of x equals 0 of multiplicity 1, then in the partial fraction decomposition of p of x over q of x, which contains a term of the form capital A divided by x minus a, that constant, capital A, can be determined by evaluating the numerator polynomial at a, the root to the denominator polynomial, and we can divide that result by the derivative of the denominator polynomial evaluated at that same root a. So using the theorem, we have p of x is going to be equal to x squared plus x plus 1. That's our numerator. Q of x happens to be x cubed plus x squared plus x plus 1 after you expand all the factors out. So we're going to take the derivative of that. Taking the derivative of q gives me 3x squared plus 2x plus 1. Now we have our pieces. When I go to find the coefficient capital A, because capital A was over the x plus I factor, we're going to plug in negative I. And we get I divided by 2 plus 2i when I plug it into that ratio of P of A divided by Q prime of A. I do the same thing for capital B and capital C. When I do it for capital B, I get I divided by negative 2 plus 2i. When I do it for capital C, I get 1/2. So our decomposition over the complex number system for x squared plus x plus 1 divided by x plus I times x minus I times x plus 1 becomes I divided by 2 plus 2i, that's divided by x plus I, plus I divided by negative 2 plus 2i, and that's going to all be divided by x minus I, and then plus 1/2 divided by x plus 1. But the question here is this decomposition actually equal to our previous decomposition when we used only real numbers? Partial fraction decompositions are unique, so this should be two representations of the same thing. They should be equal to each other. So we're going to compare our complex number system decomposition with the real number system decomposition, which happens to be 1/2 x plus 1/2 divided by x squared plus 1 plus 1/2 over x plus 1. So we're going to check to see if these are equal. We see that the value of c equal to 1/2 equals the part of 1/2 over x plus 1. So we know those are equal. So we only need to check the values of a and b. So here we go ahead and take the a divided by x plus I plus b divided by x minus I. And we combine those two pieces of the decomposition. And as you can see here, it can get pretty rigorous and pretty intense. But when we go through all the details on these two slides here, we end up with 1/2 x plus 1/2 divided by x squared plus 1. And that was our result when we factored this over real numbers. So the decompositions are indeed the same. So are irreducible quadratic factors necessary? Well, when you're working with real numbers only, then yes, they would be necessary. But when working with complex number systems, then no, they're not exactly necessary. The irreducible quadratics may be factored further into linear factors with complex roots. The theorem may be used to determine the values of the coefficients so long as that linear factor is not repeated. Thank you for your time and attention.